Hi everyone, Nate Solves Problems here with another video. This is the last video in my series on different coordinate systems. If you haven't seen the previous two, here's a link up to the playlist here where you could watch the other two, where I start with polar coordinates, then move to cylindrical coordinates, and lastly here's the one for spherical coordinates. So where does the volume of a sphere come from? It's 4/3 pi r cubed. And what is the volume element in now spherical coordinates? And truthfully, what coordinates then define a point, similar to what three coordinates would define a point in cylindrical coordinates, r, theta, and z, or in Cartesian coordinates, x, y, or z? And lastly, why are spherical coordinates important? There are a lot of applications of spherical coordinates because there are a lot of objects in the universe and in life that are spheres. Atoms can be modeled as spheres. Planets, different celestial bodies, can be modeled as spheres. So knowing spherical coordinates and being able to use it is very important. It's very helpful. Moving into quantum mechanics, you have how it's applicable to the Bohr model and to hydrogen, then to the hydrogen atom, and all of this is really important, but to get there, you have to have a good understanding of spherical coordinates and where each of the r, theta, and phi come from. Because now we have r, which can be described in three coordinates. We have theta and phi that also describe the orientation of that point in space. The volume element dv is r squared sine theta dr d theta d phi. And let's see if we can picture this. Now our radial distance is in 3 dimensions. R can be expressed as the sum of the squares of x, y, and z. As well as now phi is an angle in the xy plane. Sometimes it's reversed where theta is that angle and phi is the angle from the z-axis. But really, as long as you know which angle you're talking about and you define it one way, it is the same either way, no matter what you define it as. Just be aware of that when you're going through the problem and in your specific case. So, originally, we have already the component of polar coordinates. We have that r theta. So we can imagine that if we move r a little bit, we have that dr. If we change theta a little bit at that r, we have our r d theta. But what is that other element? We get r d theta the same way as we did before. Dr is the easy one because if we move r a little bit, we have that tiny change in r. But what's the last side? Don't be too quick to say it's r d phi. We're going to go through and really try and figure out where this comes from. So, if we have our object here, and that hypotenuse of that triangle, as seen, is r, it would have base that would be r sine of theta. And it would have height r cosine theta. And the last side, if we can figure it out, is r sine theta d phi. Because we get that base of that triangle, that's r sine theta. And if we change d phi a little bit, that angle right there, that's the arc length. That's d phi times the length of that vector, or that line drawn from the origin on the xy plane to the base of that triangle that is representing the base of the triangle that goes up to our little dv. That arc length there is r sine theta d phi. So the last side is r sine theta d phi. And what we went through is getting that other side of our cube. So now we have every component. We have each of those pieces. We have the dr, the r d theta, and the r sine theta d phi. So if we think about how we can get the volume of a sphere, if we integrate r from 0 to r, we have gone from the origin to the radius of the sphere. If we go If we follow from the z-axis from a theta of 0 to pi, we're going from the positive z-axis to the negative z-axis. And if we spin around 2 pi, we'll take that half circle with thickness r sine theta d phi and spin that around. And then we'll get the volume of a circle, of a sphere. See if you can visualize this. And now we're going to go through it. We're going to go through it step by step. If we want volume, we have to integrate dv. And we know that our volume element in spherical coordinates, which the volume element, or how we define dv or whatever infinitesimal, is going to be the hardest part with any of these integration problems. And we know that we have r squared sine theta, dr, d phi, d theta. And we can integrate r first from 0 to r. And then we have r cubed over 3 sine theta, d phi, d theta. And if we integrating d phi is easy. It's some constant times d phi, which then we're evaluating it from 0 to 2 pi. And then we do the same thing with the theta integral, and we're left with the volume of a sphere. So that concludes my series on different coordinate systems, and using those coordinate systems to really get an idea of what they mean, the volume element in each coordinate system, and using them to derive the volumes of the shapes that they represent. So thank you again for watching, and have a great day, and please let me know if you want any specific video or how I can help you to improve your understanding of different math concepts or what I can do for you. Thank you.